Hi everyone. In this particular video, I'll give you a basic introduction to the geometric and algebraic representations of vectors. So, easiest way to look at a vector would be, it's like a picture. It's like an arrow that goes from one point to another point. The first point is called the initial or tail point. The second point we call the terminal or the head point. We often then represent the vector as a sequence of two letters, the two letters being the name of the points, the first letter being the initial point, the second letter then being the terminal point, and we put an arrow over top of it. So you can think, since we have this association with a vector, with an arrow in a plane or 3 space or higher, that a vector has a length because there's a length of the arrow. We call that the vector's magnitude, and the arrow tip in some way describes the vector's direction. But the word vector originates from a Latin verb, which is to carry. So a stereotypical vector is a way to transport a point A to a point B. Now, for simplicity, I want you to think of vectors then as having two things, that they possess length and they possess direction. And for now, try to think of them as these arrows. This is misleading because later on in the term, we don't think of vectors this way. We think of vectors as a collection of objects that have defined operations which show you how to combine them to make new vectors. So what the vectors are doesn't matter. It's the relationships between them that actually matters. So the set of all points in a plane corresponds to the set of all vectors whose tail begin at the origin. So for example, for every single point A, there's a vector boldface A that goes from the origin A to the point, from the origin O to the point A, whose tail is at the origin and whose head is at the point A. I've given you a picture then of various different examples. Notice that in each case, I've labeled the vector in blue as an arrow going from the origin to some other point, and the vector's name is boldface letter, where the letter is the lowercase version of the terminal point. It's natural then to associate the vector, called as a row vector, with the coordinates of that point. So if you have the point 3, 4, we can then associate the vector going from the origin to point A as a row vector in brackets whose entries are 3, -4. The entries of the vector OA are called the components of the vector, and we often call them first component, second component, and so on. The vector, if it starts at the origin, is said to be in standard position. In this way, all a vector is an ordered list of values. But this is going to be the first of many representations of vectors. As you advance, you're going to encounter more nuanced versions. But one not so nuanced is writing vectors as a row vector is really just for typeset, because it's nice to write the vector in a row because it fits on text. But if we actually want to write it on a board or by paper, we don't do that very often. We often write them as column vectors instead. So the column vector, -2, 3, you could also write as a row vector, -2, 3. Notice as a row vector, I put a comma. You don't have to put the comma either. You just have to put enough space in so it's understood what are the entries of the vector. So as an example, let's give it point A, which is 2, 3, and the point B, 6, 5. I want to know what the vector AB is. So then that's pretty easy, because the vector AB, all it is just expressing the overall changes needed to go from point A to point B. So think about the change in X. You have to go to 6 and subtract 2. That would be the overall change to go from 2 to 6. And then you're going to 5 and coming from 3. So 5 minus 3 is the overall change to go from 3 to 5. That's the vector then, 4, 2, or just the vector 4, 2. You can also write that vector in column form. And that's it. Now the vector P that goes from the origin to the point P, whose coordinates are 4, 2, implies that the vector P just begins at the origin and terminates at that point. But what we just saw, if you look at the vector AB that goes from A, which is 2, 3, to B, which is at 6, 5, that vector has the exact same components. Looking at the pictures, the vector P and the vector AB, they look the same, don't they? They have the same length, they have the same direction. So we're going to say from now on that two vectors are equal provided that their components are equal, and vice versa. If their components are equal, then the vectors are equal. Okay, now that we have the basic idea of a geometric picture of vectors, let's talk about how to combine them. So the simplest one would then be how to add vectors. So geometrically, we think of the addition of two vectors u and v by taking a copy of v and translating it, moving it, so that the tail of v is at the head of u. That would then create the vector u plus v by going from the initial point of u to the terminal point of v. As an example, if you look at these two vectors u and v, if I want to know what u plus v would equal in terms of a picture, I would just make a copy of v so that it begins at the head of, or terminal point of u, and then I would draw a vector that goes from the initial point of u to the terminal point of v. That's the vector u plus v. Notice I'm also in this problem, I'm using little arrows above the lowercase letter instead of using boldface. That's because you can, and sometimes on a board you have to. In a textbook, we use boldface always, but on a board, you can't use boldface, so we still use the lowercase letter. We just put an arrow over the letter in order to describe that vector. Now, component-wise, all u and v are descriptions of changes in entries in the different components. So then if you want to know what the vector u plus v is, it would just be the sum of those changes. So literally, if you want to add two vectors, you just add the components. That's what that definition says. Likewise, you can also form what's called the scalar multiple of a vector. So if you give me any real number and any old vector, you can define the scalar multiple of the scalar times the vector as the vector where you just literally multiply the scalar through the components, like it distributes. I've drawn a picture to show you what happens. So in red, I gave you the vector u, and then I drew in gray the vector 1/2 u, 2 times u, negative u, and also negative 3/2 u. Hopefully you notice from the picture that what seems to happen is that the absolute value of the scalar tells you how much the vector's length changes. And if the scalar is negative, it reverses this direction. But if the scalar is positive, you stay in the direction of the original vector. You'll see that that's actually true in general, but I have to explain why. To do that, though, we need a definition of length, which won't happen until the next set of videos. In general, the scalar is called, the constant multiplication is called the scalar of the vector. Now that we have addition and we have scalar multiplication, we can put them together to get vector subtraction. Because vector subtraction, just like with real numbers, there is no such thing as subtraction. There's only addition of opposites. So if you want to subtract two vectors, basically all it says is just subtract the components. But you need a picture way to view it also. So suppose you have two vectors, a and b. I've drawn them so they start at the exact same initial point. What I want to do is draw in the vector a minus b. To do that, I need a copy of a somewhere, and I need a copy of negative b. So now negative b, remember, just reverses direction, but it's the same length. So I'm going to put a copy of a so that its initial point is at the terminal point of b. And then I'll put the vector negative b so that its initial point is at the terminal point of my copy of a. So then you can see from this picture, we can now draw the vector a plus negative b, which is right there. It's the vector going from the initial point of a to the terminal point of negative b. Notice though that the outside vectors form a parallelogram. And in fact, The addition of the vectors a plus b is the other diagonal of this parallelogram. We call this the parallelogram rule. If you draw the vectors a and b, so they start at the exact same initial point, and then you just make copies of them in order to make this parallelogram, the addition is the vector that goes between the vectors, and the subtraction of the vectors is just the other diagonal. You just have to go in the right direction. Notice that the arrow points to the vector that's being added. So you have plus a minus b. You go towards the terminal point of vector a and away from the terminal point of vector b. All right. Now, we can't draw vectors if we add on too many more components. I'm only ever drawing vectors in a plane, so we have only two entries, the first and second component. But you can naturally extend this up to however many components you want. So if you have a point in what we call Rn space, that's the set of all points that has n entries to them and coordinates to them. You can associate to that point a vector, and you could write that vector either in row form or in column form. The individual entries of that vector are just called the components, and we often refer to them as the ith component for the ith entry. We'll use v sub something to talk about the something component. So v sub 1 is the first component of the vector 1, of the vector v. The number of components are not known unless you specify the space R something. So if it's R3, there's 3 components. If there's R5, it's 5 components. We can't draw those vectors once you get to the 4th dimension, but you can still get an idea of it. Also, another vector that you can't draw in general is the 0 vector, because it begins and ends at the same place. There's not an arrow there. But still, that's a vector that describes a certain amount of change. It's literally the vector of no change. So we'll use in general the bold-face vector 0 as the vector whose components are all 0. Notice that you just can't draw that. Also, now that we have these vectors, you can then naturally extend the definition of vector addition and scalar multiplication up to vectors of many, many components. You literally just add the components together or multiply the scalar through the components. Just as a quick example, if I gave you the vector 2, 3, 1, and I want to add to it the vector 2 times the vector 1, negative 1, 3, this is then the same as writing just do everything by components. So it'd be 2 plus 2 times 1. You'd have 3 plus 2 times negative 1. You'd have 1 plus 2 times 3, which is, of course, the vector 4, 1, and 7. That's the vector in column form. Okay, so as I mentioned or hinted at earlier, later on in the course we're going to talk about vectors as just objects. We're not going to describe them so much. We're going to worry more about the operations that connect them and the properties those operations have. The only thing we really need with vectors is to be able to combine like terms. So we need a list of properties that vectors have to have. These are the properties that vector addition and scalar multiplication must have to do I want to combine like terms. So that would be these properties. The first one is commutativity of addition. The order of addition doesn't matter. The next one is associativity of vector addition. You can change the order that you wish. Notice that the order of the vectors here, u, v, and z, don't change. But the order in which you do the addition does change. That's what the association does. Also, you have vector addition, the vector identity. If you take u plus the 0 vector, you just get u. And of course, by the first property, that means 0 plus u is also u. You have the vector annihilation, or the additive inverse property, that u plus negative u, which is just u minus u, that's the 0 vector. If you take a scalar times a sum of vectors, the scalar would distribute through the vector addition. The next one is that if you have a sum of scalars times a vector, you can distribute the vector through the scalars and then add that afterwards. Number 6 is one of those that people look at and go, well, yeah, that's true, that's obvious. But there's something really weird happening in the 6th one. Notice that the left-hand side of that equality, the addition is between real numbers, while on the right-hand side, the addition is between vectors. The addition operation is actually between different objects. So that's very interesting that we can do that. The next one is reassociate scalars. So c times d times u, you can just multiply the scalars c times d first, and then you multiply that to u. And then lastly, if you ever take the scalar 1 times the vector u, you just get the vector u. Now this list of properties, especially the last one, because 1 times u, all you're doing is distributing the 1 through the components, people think are very, very obvious. But in general, later on, when you don't know what the vectors are, how to describe them, having the ability to say that 1 times u will be the same as u is an important algebraic step. All these properties are the critical skills we need to be able to add like terms of vectors. I'll show you what I mean. Let's go ahead and look at an example of how to use these properties. These are things that you have used all your life in algebra. You have just skipped over actually saying them because it takes too long. A lot of algebra is designed to crush down these particular properties to do them quickly. We just say the work instead. You might want to take a moment and write down these properties. 1, 2, 3, 4, and so on. I've mentioned their names, but the actual names don't matter, not really. If you want to refer to them in homework, though, it's useful. So let's look at an example. The vector x here is unknown. I want to know what the vector x equals in terms of the vector a. So the vector x will then be some scalar multiple of a. I just want to know what it is. Now you can go, I'll just treat it like algebra and just multiply things and add things in both terms to solve for x, like you always would. But that's not what I want you to do. We're going to use the properties that you just saw really slowly. This is the right way to do the process. Again, in algebra, we skip all of this, but this is the right way to do it. So, I want to solve for x. I will do things on both sides of the equality in order to cut down the number of steps. After a while, though, I'm going to say, I don't want to keep going. I just want to get to the answer. And I'll just write down what you think the answer is. So the first step is, I'm going to take 5x and minus a and reverse their order because of commutativity. I'll take 2 times the vector a plus 2x and I'll distribute it through. Notice, though, I didn't take 2 times 2 and make it be a 4 because that's a different property. So on the left-hand side, I use property 1. On the right-hand side, I use property 5. Next, on the right-hand side, I'll take 2 times 2x and I'll write it as 4x because I can reassociate the scalar multiplication first to get 2 times 2, 4, and just write it by and just multiply it to x. Okay, so the next step is I want to, again, solve for x. So what I'll do now is I will subtract 4x on both sides. That's just a property of equality. If two things are equal, you can add the same thing to both sides and the result is also equal. Next, I will then reassociate. Notice that I did not automatically just write 4x minus 4x and cancel them. I'm going to have to do that work to explain how that happens. So on the right-hand side of the equality, I reassociate the sum so that I take the 4x minus 4x first. I'll then add the result to 2a. I'll do the exact same thing on the left-hand side of the equality. I reassociate. Again, though, you got to be really careful. So on the right-hand side, the right way to do it is to say 4x minus 4x, that's the 0 vector. So I replace that with the 0 vector. That's property 4. And on the left-hand side, this one's really hard to see. You have to collect the scalars together. That's actually distribution. That's doing the act of factoring out the x instead of distributing it through the scalars. So 5 times x minus 4 times x is equivalent to 5 minus 4 times x. Now, On the left-hand side, 5 minus 4 is just 1. So we know that 1 times x is, by property 8, x. And we know that 2a plus the 0 vector is just 2a. So all those steps are the process of getting rid of 4x by subtracting it on both sides, just by doing the process really carefully. You don't really want me to keep doing this. So here, if I wanted to solve for x, I would add a on both sides. On the left-hand side, a and negative a would become the 0 vector. I'd have 0 vector plus x, which is x. On the right-hand side, I'd have 2a plus a. I could write that as 2a plus 1a, because I need a scalar. I could then write that as 2 plus 1 times a. That would then be 3a. So then by doing all those steps in different properties, you would get then that x is 3a. And that's the answer. I know it's awful, isn't it? But these are the properties. Those 8 that I gave you, those are the properties that allow us to do the add like terms and cancel things in equations. They're the only things we need. And that's really the only properties we need for most of the entire course. After that, it's just definitions and proving things about these properties and how they interact with other definitions. This here, these properties, that's the basis of linear algebra. So in this video, we're going to talk about the basic building blocks for linear algebra, which we call linear combinations of a set of vectors. It's just a way to go and use the basic properties of vectors, vector addition and scalar multiplication, to form a new vector. So a linear combination. We say that a vector v is a linear combination of the vectors v1, v2 up to vr if there are scalars c1, c2 up to cr. So v is a sum of the scalar multiples of v1 through vr. c1 times v1 plus c2 times v2 all the way to plus cr times vr. So you're going to need an example to understand that. So is the vector 2, 3 a linear combination of the vectors e1 and e2? e1 being the vector whose first component is 1, everything else is 0, and e2 being the vector whose second component is 1, and everything else is 0. The number of entries or components to the vector e1 depends upon context. So if we're talking about a vector that has only 2 components, e1 has 2 components. If we have a vector, we're discussing vectors that have 3 components, well now e1 has 3 components. So those vectors, they change. Now you can probably just look at it and see, but this is asking then, is there scalars c1 and c2 so that the vector 2, 3 is c1 times the vector 1, 0 plus c2 times the vector 0, 1. Now looking at it, I'm sure you can figure out the scalars are c1 is 2 and c2 is 3. I'm pretty sure you can look at it and see that. Don't think of it just computationally. Remember, there's a geometric connection too. That makes things a lot easier to understand in the long term. So when you see c1 times v1, that's a multiple of that vector. It changes its length. When you see c2 times e2, it changes the length of e2. When you add those multiples, you are adding those new vectors tail to head. So let's go draw them. So 2 times 1, 0 would then involve looking at a coordinate grid where e1 and e2 define the x and y axis and define for you the rest of the grid. e1 is the horizontal vector, so 2 times e1 is the blue vector going this way. 3 times e2 is the blue vector going that way. So then 2 times e1 plus 3 times e2, when you put those vectors tail to head, you get the vector 2, 3. So that's what's happening in this case with linear combinations. You're, in a sense, going and forming a sum of vectors to be another vector. Don't think of it just computationally. There's a picture, a geometric idea behind it. So we then say the scalars formed in that linear combination are called the coordinates. They're the coordinates of the vector 2, 3 relative to the vectors e1 and e2. Notice that for the vectors e1 and e2, the coordinates of the vector relative to e1 and e2 are actually just the coordinates of the vector itself, because C2 was 3 and C1 was 2. That's not actually always going to be true, as you'll see in a minute. Let's try it again, though. Can you find any linear combination of the vector 1, 2 of the vectors using the vectors 0, 4, and 1, 0? Yeah, easily. Because notice, if I want to find that, I could say the vector 1, 2 is just equal to, it's 1/2 of the vector 0, 4 plus, that'd be 1 times 1, 0. So that's the linear combination. I gave you the scalars that form the linear combination of the vectors 0, 4 and 1, 0 that adds up to the vector 1, 2. So I could say that the coordinates of 1, 2 are 1/2 and 1, but relative to the vectors 0, 4 and 1, 0. Notice that I did not reverse the order of the vectors, because you can't. It's understood that when you give me the list of vectors that you can't change the order. So the scalars have to be in the exact same order. So the coordinates of the vector 1, 2 are now 1/2 and 1 because of the order of the vectors I gave you to form that linear combination. Neat, right? Okay, let's take that idea and extend it. Let's suppose that you have the vector u, which is 2, 0, and the vector v, which is 1, 3. I want to know, is the vector 4, 6 a linear combination of u and v? Remember now, that means I need a scalar times u plus a scalar times v, that when I take the sum of those scalar multiples, I get the vector 4, 6. I want to give you a geometric idea of what's happening here, so that you can think of it conceptually and answer more interesting questions. Think of it as if the vectors u and v actually create a new set of axes and their own version of a slanted coordinate grid. I'll draw a picture to help you out. So here's the system created by E1 and E2. E1 is the x-axis, it makes the x-axis. E2 makes the y-axis, at least multiples of it. And from there you can draw in the vector 4, 6. Over top of this system, you could easily draw the vector u and v. Now, u and v, though, they point in a direction, so they make lines. These two lines meet at the origin. Okay, now don't get rid of those blue lines or the vector u and v, but erase the coordinate grid and erase the horizontal and vertical x and y axis. Okay, now from here, look at u and make copies of it in order to mark off 1u and 2u and 3u and -1u, and do the same thing with v along that line to mark off 1v and 2v and 3v. By doing so, you actually create two number lines. Using those number lines and parallel lines parallel to these blue lines, you make a coordinate grid. Notice that the vector 4, 6 falls on the node of one of those points in the coordinate grid. Looking at the picture, you can tell that the vector 4, 6 appears to be 1u plus 2 v's. And in fact, if you check out the arithmetic, that's exactly right. So, by looking at the picture, you can then say the vector 4, 6 is a linear combination of u and v, and the coordinates of the vector 4, 6 relative to u and v are the numbers 1 and 2. We often just call the coordinates a vector itself, which is 1, 2. This is neat because that means I gave a different name to the vector 4, 6. It's also the vector 1, 2 relative to the vectors u and v. Hopefully also you can see that if I were to draw any vector, not just 4 and 6, but any vector, I could still create this slanted coordinate system and find coordinates of the old vector in terms of the vectors u and v. The vectors u and v in some way kind of span the whole space. That is a topic that we will get to later on. And that's enough for now. That gives you a basic introduction to the algebra and computation of vectors in Rn, and a geometric understanding of what those operations mean. and how to put them all together to form linear combinations of vectors to get a new vector, and also that linear combinations is some way to create like a new coordinate system for the space.